It is with great pleasure that I would ask Scott to join us on stage.
All right, thank you very much, Rick. I appreciate that very much. So people ask me all the time, do you speak a lot? Do you get nervous about speaking? And my response, at least for today, is when you have weather like this and you're in a venue like this, it really doesn't matter what you say. At least that's my perspective. So I'm going to get right to it, and I'm just going to forewarn you that it's a technical presentation. And as a futurist, I was at IBM last week in Las Vegas as an IoT futurist, talking about not 1 to 2 years, but what's going to happen in the next 5 to 10 years. And the reason this is important is if you're making difficult and strategic decisions in the next 10 years out, topics like quantum computing is going to be very germane to your strategic roadmap, because you may be thinking that it's an infeasible theoretical body of framework, when in fact it's actually very much in practice. And that's what I'm going to talk to you about today. So one of the things that's very interesting about humans is that we're skeptics. I'm from the US, and people always ask me about Trump, and I just cringe and try to avoid some topics. But we're just natural skeptics as people, whether we're talking about climate change, religion, or science. It really doesn't matter what it is. Now, here's what people said about computers about 6 years ago. I think that there is a world market for maybe 5 computers. This was said by Thomson Watson, Chairman and CEO of IBM in 1943. Computers of the future will weigh no more than 1.5 tons. Popular Mechanics, 1949. Well, it's easy to laugh at some of these comments today, but back then they meant what they said, and so did many others. So, speaking out, where are the 1.5 ton computers? Well, fortunately, we've actually managed to get down to just 1 millimeter cubed that sits on the edge of a coin. The Michigan Micromates, or MOTES, is one of the smallest autonomous computers in the world. And the researchers at the University of Michigan worked on M2M specifically to support things like the Internet of Things, so that objects like toasters and refrigerators and doorknobs can actually have intelligence. Now, despite the size that you see, it's actually a full computer. It's able to take pictures and temperatures and record pressures. It can actually be even internalized or injected into the body. Again, many of you here are skeptics, and that's just the way I like it. Well, just look at this D-Wave quantum computer. At least that's what they claim to be. By the way, do you see the similarity with the IBM mainframes from the turn of the century? Or 1960s, I should say? Well, the question is the D-Wave computer actually a quantum computer? Well, sure, it may solve problems, but what if the noise was disentangling the qubits? Well, then it's just a fancy classical computer, which is another term for the computers that we use. Well, to test this, Daniel Lidar, a quantum scientist with USC, ran thousands of instances of a problem of the D-Wave that charted essentially a chart in terms of the success of probability. Well, the final curve looked something like this, a U-shape, which basically meant that it entirely succeeded or entirely failed. Now, if you were to run a classical computer, you get a very different result. It's a normal distribution curve that you're familiar with. Well, clearly, the D-Wave didn't behave like a classical computer, but is there evidence reasonable enough for us to believe that it's quantum behavior? Well, they actually tested against an Intel machine. And it turns out the D-Wave is actually not faster than an Intel desktop computer. So it had absolutely no evidence of quantum speedup. So you're probably thinking, quantum computer, that's just purely a theoretical quantum physics branch. And we'll probably never see it in our lifetime, right? That's exactly what I'm sure some of you are thinking, or should be thinking. Well, to the dismay of skeptics like yourself and myself, there are actually serious and tangible progress being made towards quantum computing. What you're seeing on the screen is a blueprint. It was a research led by Professor Winfried Hensinger, head of the Ion Quantum Technology Group at the University of Sussex. And they believe they finally overcome one of the main technical problems that have prevented the construction of a very large-scale, arbitrary quantum computer. Now, in their publication on the science's advances earlier this year, they show a blueprint for a microwave-trapped ion quantum computer that would actually enable large-scale QC. Now, what makes this approach very interesting is it's a modular approach that makes for a scalable quantum computer. And it's an architecture based on long wavelength radiation quantum gates. And the modules control all the operations, all in a standalone set of units. And the great thing is all of this is constructed using current technology. Now again, this is not a small quantum computer. This is the engineering blueprint to build out a full-fledged quantum computer. Now the problem with today's partial QC is that they require these lasers to focus precisely on these individual atoms. And the larger it gets, the more lasers that you need in order to have that precision. In particular, something called deep coherence. Well, they are actually using a different technique that involves a microwave field and electricity in an ion trap device. And this allows for that scalability that I'm talking about in a QC. Now, for those of you that are here, you're interested in Internet of Things, not quantum computers. Well, let me tell you, or share with you, some of the major obstacles that your firm, perhaps as a provider, or your firm as a customer, are asking to solve. Some of the biggest challenges that we have that's hampering the broad-wide adoption of Internet of Things can be potentially addressed by quantum computer. Now what you're seeing on the screen is World Economic Forum, where some of the obstacles include, as not surprising, security. One of the biggest issues that's a crippling issue, whether we're talking industrial or on the consumer side, that face Internet of Things. Then there is privacy, which is a heightened issue with GDPR and in Europe. That also has impacted privacy and the cost of investment and the perception of risks that are unknown. All of these things. And of course, it's the standards and protocols, the interoperability or the lack thereof, and the fragmented world that we live in when it comes to Internet of Things. Now the next slide shows you, maybe a little bit hard to read, it gives you a further breakdown on some of the issues related to security, encryption, and the need for higher computational power. Because we're not just talking about large volume of data, but what do you do with that data? If you're talking about a smart city or industrial Internet of Things, we're talking about solving very complex optimization problems. Well, before we can address quantum computing and how it may potentially help some of these challenges that we face in the Internet of Things, we first need to get some fundamentals on quantum physics and quantum computing. Now, quantum mechanics, as some of you are much more qualified than I am, is a branch of physics, which is the fundamental theory of a nature at very small scale and low energies of atoms and subatomic particles. By the way, my daughter, who's was in middle school, she's singing these songs that helps her to memorize an element of tables. It's just incredible. She's able to recite it in literally 2 minutes. Well, classical physics, the physics that existed before quantum physics, they're more interested in the approximation of what we call macroscopic scales or large scales. Well, quantum mechanics differ in that they're more interested in the things that are at the discrete values or the quantization. Objects that have characteristics, both particles and waves, or what we call wave-particle duality. And there are limits to the precision in which quantities can be known because we're talking about very small subatomic level. And we call that the uncertainty principle. In quantum mechanics, what we're talking about is a discrete unit assigned to certain physical qualities and quantities such as energy of an atom at rest, or the discovery of the particles, or that these are discrete packets of energy and wave-like properties. It underlies a mathematical framework of many of the fields in physics and chemistry, such as the condensed matter physics, or solid-state physics, or even atomic physics. Quantum mechanics was initially developed to provide a better explanation and the description of an atom, especially in terms of the difference of spectra of light emitted by different isotopes of the same chemical elements, as well as that subatomic particles. Now, the quantum mechanics incorporates 4 classes of phenomena for which classical physics cannot account for, such as quantization of certain physical properties, quantum entanglements, principle of uncertainty, and like I said, the 4th, wave-particle duality. Let's talk about quantum superposition. One thing that's really exciting about quantum computing is this notion that you can actually be in multiple states. Wow, I wish I could be like that, especially when it comes to my wife, because I can't do the dishes and take out the garbage and watch the kids and everything else. But what's really cool is you can be here and there, sideways, left and right, all at the same time. I mean, it's incredible. Talk about multitasking. And it's free from the binary constraints that we typically associate with when we talk about traditional computation. See, the traditional computing model takes the binary approach, right? The bits, 0 and 1. Well, in quantum, we talk about something called qubits, which is 0, 1, and both simultaneously. That means that if you have 2 qubits, you can have 4 values all at the same time. 0, 0, 0, 1, 1, 0, 1, 1. Let's talk about quantum entanglement. Now, this physical phenomenon that occurs when pairs or groups of particles are generated or interact in such a way that the quantum state of each particle cannot be described independently of the other. So it's kind of like your soulmate. No matter what you do, even if you decide to move away, you are just tightly correlated. And it doesn't matter that distance, including one end of the universe to the other end of the universe. The quantum state describes a system where there is this, almost this way that you cannot be completely independent of each other. Beautiful. I think we should make a love story out of quantum computing. Quantum systems can become entangled through particles with less than 1/100% of travel time of speed of light. Now, in other words, what that means is, yes, it can quite reach the speed of light, but very close. And this has huge implication to telecommunication, to cryptocurrency, and crypto algorithms. But this notion of being able to measure the effect almost instantaneously is one of the key foundational benefits of QC. Now, equally interesting is that if we were to actually try to separate out these 2 entangled particles, when we measure these particles, we find that the result of the measurement of the first and the second particles will almost match exactly. It's just that they will be in opposite values. Now, among the best known applications of entanglements are quantum teleportation and superdense coding. I gave this presentation a couple of weeks ago, and somebody said, wow, teleportation? Now we're talking. Star Wars, Star Trek? No, that's not what I'm talking about. But we are talking about still nonetheless very exciting things. Quantum teleportation is a process by which the quantum information, such as exact state of a particular atom or photon, can be transmitted from one location to another location. With the help of a classical communication, previously shared quantum entanglement between the sending and the receiving location. Now, it does depend on classical communication, but, like I said, it can almost reach that speed of light. That's pretty exciting. And it makes for the feasibility to teleport one or more qubits of information between two atoms, two entangled atoms, without actually fundamentally changing the elemental level. Now, the other piece of it that's really very exciting, especially for security purposes, is that the quantum information that gets transmitted cannot be copied or destroyed. Matter of fact, just the sheer fact that you're looking at it will actually change the result. And this has huge implication to the ability to actually be able to detect if somebody's trying to hack your system. Now, quantum teleportation provides a mechanism for moving those qubits from one location to that other location, like I said, but without actually physically transporting the underlying particle. Okay. Well, much like the invention of telegraph, allow for classical bits to be transported at high speed across continents, quantum teleportation holds the promise that one day qubits could be moved through open space. And I'll talk to you a little bit about this experiment that the Chinese are doing with the satellites. Now here's an illustration just to help kind of cement the concept that I'm trying to share with you. If Alice, on the far left, has a particle which is entangled with a particle owned by Bob, and then Bob then teleports that to Carol, well then afterwards, Alice's particle will be entangled with Carol's. So in other words, the state of Bob's first particle can be teleported to Carol's, although Alice and Carol never interface or interacted directly with each other, but now they're entangled. Let's talk about cryptography, which I think is probably one of the most relevant and applicable areas that quantum computing can address. Because we're talking about a shared noise of entanglement, one of the things that's really interesting, like I said, is the simple measurement of that entanglement will actually change the result and can easily detect the presence of an interceptor. The best known example of quantum cryptography is probably the quantum key distribution, which offers this information that's theoretically secure solution to the key exchange problem. Now, the quantum key distribution is processed by using quantum communication to establish a shared key between two parties, without a third party actually learning anything about that key whatsoever. And if a third party tries to eavesdrop on that communication between the two parties, well, guess what? Like I said, everybody will know, and that result will actually change. Once that key is established, it's used for encrypted communication using classical techniques. Now, today we use very popular public key encryption and signature schemes like RSA, right? Well, they can be easily broken by quantum computers using the Shor's algorithm, if you're familiar with that, for factoring and computing discrete logs on a quantum computer. Now, the advantage of quantum cryptography lies in the fact that it allows for this completion of various cryptographic tasks that are proven and conjectured to be impossible using today's computers. It's impossible to copy data encoded in a quantum state, and the very act of reading that data encoded in that quantum state changes the state. And this is part of the fundamental benefit of this quantum key distribution. All right, so let's get into the quantum computing. I've alluded to it, but I didn't actually explicitly define this, but let me just get into a little bit more. Quantum computers are different because of this notion that, unlike the traditional computers, it's not binary, where we're talking about bits, right, 0 and 1. Quantum computation uses quantum bits, or qubits, we call them, which has a superposition of states. Remember that state I told you about? 0, 1, or any combination? And you're seeing here in the circle, or the sphere, I should say, any point within that sphere. A quantum Turing machine is a theoretical model for such a computer, and it's known as a universal quantum computer. Now, large-scale quantum computers would theoretically be able to solve certain problems quicker than any traditional computers that we use today, such as integer factorization using Shor's algorithm, or the simulation of quantum many-body systems. Now, there are other algorithms like the Simon algorithm that you can run as well for solving any number of probabilistic classical algorithms, almost, like I said, instantaneously. Quantum computers are able to efficiently solve Internet of Things, optimization problems that are frankly not feasible using traditional computers. Now let's talk about some of the problems that we have in quantum computers. There's something called quantum decoherence, which is truly the Achilles heel of quantum computing. And in the field of quantum, error correction, trying to stab off that decoherence is probably one of the biggest challenges that we have today. And it's, for instance, exactly why we're having to struggle with a large-scale computer. Now let's talk about the degree of quantum decoherence. Now, there are other sources of decoherence besides environments, including things like the quantum gates and lattice vibrations and background thermal nuclear spins and the physical systems used to implement these qubits. Now, this decoherence is irreversible and it has to be controlled. Otherwise, you start to lose that entanglement. So let's talk about IoT, and how does this benefit IoT? Well, let me just first set clear expectations. Quantum computer is not a silver bullet point for solving all problems. That's not what I'm saying. But rather, I'm presenting possible areas of benefits, and it serves as a rally call to the industry to start to explore. And it was interesting to see the chairman and CEO of IBM, Ginny, mention, aside from AI, quantum computers last week. It really requires all of us to dig deeper. And like anything, you're not going to really know the extent of the benefit until you put it into practice. Now, in terms of security, it's this notion of integer factorization which underpins the security of public key cryptographic systems. And it's believed to be computationally infeasible using today's computers, especially when it comes to dealing with large integers. Well, if they're the product of few prime numbers, such as the products of 200-300-digit primes, very difficult to solve. Well, quantum can solve these problems. Well, by comparison, quantum computers could efficiently solve these problems using the Shor's algorithm to find these factors. And it has this ability to allow for quantum computers to decrypt many of the cryptographic systems that we use today. Now, in the sense that it will be a polynomial time algorithm for solving these problems. The other thing that's really exciting is not only can it hack and break today's cryptography and algorithms, is that once you actually build it in a quantum computer, other quantum computers cannot actually break it. Now, one of the most popular public key ciphers are based on the difficulty of factoring integers, like I said, or that discrete long problem, both of which can be solved using this Shor's algorithm. And these include things like RSA, Diffie-Hellman, and other algorithms that some of you are familiar with. All right, let's talk about computation. How fast can this thing really go? And what can it do for us? Well, it can actually harness the quantum states to represent bits simultaneously for exponential growth in speed improvement. And the benefits of that means that you can solve enormous, complex problems in a very reasonable amount of time. Now, this is very relevant for IoT data, and because many times we're trying to solve an optimization problem, fleet management, asset management, oil and gas, utilities. Well, based on the quantum level, we were actually able to program atoms to represent all the possible input combinations and do it all simultaneously. So instead of just stripping of bits, binary bits, you could literally take all the combinations of inputs and just send it. And then immediately we get a result back. It means that with a regular computer, you have to run these serial cycles, right? Well, they're very slow. It takes a long time. And depending on the problem you're trying to solve, it can take literally the end of ages. Whereas quantum computers can offer up polynomial speedups. And of course, the most well-known example of that is quantum database search. Let's talk about interoperability. Well, today's IoT standards are really constrained to the radio frequency or wavelength capabilities. This is exactly why we have so many different protocols and standards. Because we have no easy way of handling it, especially when it comes to energy constraints. But with quantum computer, that goes away completely because you're not restricted by the data rates, you're not restricted by the range, or even the fragmentation of standards and the power constraints that we have today. It also enables quantum teleportation to send quantum information from one location to another, and it's really not limited by any distance. And it really doesn't matter if you have satellite, if you have cell towers, it does not matter because though it does depend on constant communication channels, it will actually operate at almost fastest speed of light, almost, but not by reaching that. So what that means is that you won't have the latency choking points that we have today that even 5G is trying to attempt to solve. Now, some of you are probably thinking, well, a quantum computer is so theoretical. Would it actually be able to get to a miniaturized state? Well, remember, 1960s, what did people say about traditional computers? And now we've got this 1 millimeter cube and cube, right? Well, there's a potential that in the future, this is a little bit further out, quantum computers can actually become miniaturized to the point that it can actually reside locally on the edge. And that provides quantum computing power. And what this means is, already today, we can actually run localized AI and machine learning on the edge to an extent. But in the future, now we can actually run advanced deep learning capabilities right on the edge. And it will rival, if not exceed, the capabilities of cloud-based AI systems. I'm going to talk about storage a little bit later, in just a few minutes, but there is also an opportunity to increase storage capacity significantly. All right, so you're probably thinking, well, this is great. All theoretical, lots of math. Well, actually, no. This is not years away in terms of decades. But what we're talking about is that there's active development and a potential for a full-fledged quantum computer is about 10 years or less. IBM puts it at 8, others puts it at less than 10 years. Now, like I said before early on, I mentioned that there's a blueprint for a microwave trapped ion computer, quantum computer. Now, this prototype is going to be available as early as in the next couple of years or more. Okay? So again, it's not that far off. In addition to that, China, if you've listened to the report last year, they actually launched this communication satellite up in space. And what they're doing is they're actually testing the fundamentals of quantum communication. It's a $100 million USD quantum experiments at the space scale missions. And for the next 2 years, they're going to actually demonstrate the feasibility of quantum communication between Earth and space. So if you're thinking about laying fiber optics after fiber optics and have a 20, 30-year plan, you might want to think about kind of the next 10 plus years. Because again, it can travel at any distance. It's not constrained. The latest research, just before coming to this conference, was that there's a discovery of a new state of phase of matter, and it's called time crystals. And it was published in the journal Nature. And what they actually were able to do, they were able to create and observe time crystals, which are long theorized quantum systems that can spin at their own pace, independent of the environment. And it seems to break the rules of the normal sense of timing. Now, researchers believe that this research is very important. The underlying physics and technology is very important because it can actually help them to build much more sensitive quantum sensors. Because what it means is that with time crystals, the decoherence issue that we talked about, or the coherence time, meaning that the message stays longer, that relationship stays longer, will actually maintain that relationship and the density of quantum qubits much longer, and it's very more substantial. So that it doesn't have the notion of that decoherence and melt in milliseconds that we have with issues of today. The last piece I'll share with you is that researchers at the Swiss Federal Institute of Technology published in Nature a few months back that they've been able to actually put single active magnets to make an atomic hard drive. The rewritable device made from these such magnets can actually store 2 bits of data, right? Well, with the quantum qubits approach, they can actually scale up to increase that hard drive storage capacity to about 1,000 times. And now, again, I'm not going to go into too much of the science behind it because I'm running out of time, but that's incredible, and that's important for edge computing and the storage capacity that edge and decentralized computing will support down the road. So in sum, quantum computer has the potential to supercharge computation, and certain types of computation specifically, like Shor's algorithm. And it provides this notion of instantaneous data communication over any distance without the traditional constraints that we face today. You can actually break some of the hardest cryptography as well as build hack-proof security even from other quantum computers. Now, instead of saying, like most skeptics, this is not real, I hope that this will interest you enough to explore the possibilities of quantum computer for your organization. So with that, I want to thank you for your time.